This will be the second talk by Professor Inkang Kim from KIAS. His title is Bulging Deformation and Topological Entropy.
Okay, thank you for staying with us. The second part is about the even though the volume of the projective surface goes to infinity, topological entropy remains bounded below from zero. Okay, that is our goal. So what is the construction? It's called bulging kind of construction. If you have a surface and if you have a gamma, some simple closed loop, then you can decompose fundamental group into this amalgamation. So if gamma is separating, then the left-hand side, right-hand side, amalgamated along gamma, okay? Or if it is non-separating, you write it down as an H-N extension. And then this gamma, it will be a hyperbolic surface, hyperbolic isometry. So you can diagonalize it here, and satisfy this condition. So suppose there's some strictly convex real projective structures on the surface, then you will have a holonomy, and you want to conjugate the right-hand side by some matrix, Why this black bar does not disappear? I'm not sure why it does not. How can I?
Yeah.
Okay, disappear. So I want to conjugate this representation using this matrix. So this matrix is diagonal matrix, and you expand along the second coordinate, then you kind of contracting along the first and third one. The picture is maybe easier. So this was a gamma, okay? And suppose that we are dealing with a separating case, then you will have a bunch of like countably many lift of this gamma, and you choose one here, gamma tilde, some specific one. Then holonomy of this gamma is some kind of an isometry like this. And if you write down the coordinate in terms of the eigenvector of here, in terms of an eigenvector here, and this is a mutual point, fixed point, you can obtain by drawing tangent line here and their intersection point. So what this matrix does is you stretch toward this direction, you stretch. So the original omega was here, and if you stretch along here, that will be stretched like this. You know this dashed circle here, okay? So depending on whether S is positive or negative, but we are dealing with only when S is positive. So you sort of pull this guy toward this second direction. That's why it's called bulge, you bulge. But you have to this bulge for every lift of this gamma, okay? So here you bulge a little bit, then this will be bulged here and bulged here. And you do all this thing here. And intuitively, you can see When S goes to infinity, if you bulge and bulge and bulge, the limit domain will be like attaching this triangle here. Okay. So at the limit domain is kind of properly convex, but not strictly convex. And you attach all these triangles for the lift of this gamma. This is called the bulging deformation. And the Goldman, he studied this kind of things, and he left this as a forever preprint. I think you can probably download his paper from his website. Okay, so this is a bulging deformation along some gamma, and you do the similar thing for non-separating curves. And the convention is we do bulging on the right-hand side. Right-hand side mean it has an orientation. Surface has an orientation, and gamma has an orientation. Right-hand side mean, if you walk along the direction of gamma, your right hand will toward this point. So you bulge it. So the lift will have a canonical orientation of gamma. You always bulge here on the right-hand side. Okay. Then the limit domain is kind of attaching all these triangles. This is a bulging deformation. So, but here, KL means the left-hand side and right-hand side. What is the left-hand side of this domain? So you take out all this part and lift all this gamma, and then you cut out all the right-hand side of this lifted gamma. Then what is left with is on the left-hand side is KL and KR. Okay, you see the bulging deformation is just the conjugation on the right-hand side here. So because this is a conjugation, all the geodesic appearing here, and all the geodesic appearing here, they will have the same length. It's just a conjugation. The problem is when geodesic is going left and right also. Okay. But if the geodesic stay only on right-hand side or left-hand side, all the geodesic length will remain the same. But when geodesic going from left to the right and so on, then after you bulge, the length will goes to infinity, because bulging usually entails like inserting some kind of almost a flat cylinder along gamma fins. And the action of the, let's say, rho S, this is a holonomy representation of the bulged structure. Rho S acts as the same on KR, KL, and KR during the deformation. All this kind of, there's some part. And we take a like Gromov-Hausdorff limit of these structures, but it's important whether you choose a base point on the left-hand side or right-hand side. If you choose the base point on the left-hand side, all you see in the limit structure is just this this triangle. So right-hand side will disappear in the limit. All you see is this thing. And if you quotient out by the action of gamma, you attach infinite half on a cylinder. Okay, so if you choose the base point, the Gromov-Hausdorff limit will be something on the left, and the right-hand side will disappear, and you only see the half-infinite cylinder. And it's the same thing when you take the base point here, and you can do the debulging on the left-hand side, and you see the same pictures. Okay, so omega is the open domain associated with the bulged structures. there's always, for example, KL sitting inside it is in omega S, and this omega B infinite, the limit structure, it's obtained by attaching all these triangles to omega. So if you do the bulging and analyze what's going on carefully, this is the limit structure. Okay? So when gamma is separating, we let the bulge parameter S goes to infinity. So what is this bulge parameter? Did you learn the hyperbolic surface and Fairchild-Nielsen coordinate? What is the Fairchild-Nielsen coordinate? You take 3G minus 3 simple closed curve to decompose the surface into pairs of pans. But these pairs of pans, the hyperbolic structure on pairs of pans, are determined by the length of this 3 cuff, right? If you specify the length of this 3 boundary, then the hyperbolic structure is defined. So you need like 3 parameters, positive real parameters, to measure the length of this cuff of pairs of pans. And then you start to glue the pairs of pans along this common geodesics. But there are, many ways to glue this thing. You can glue it like this, you can twist it, or you can twist on the left hand like this. So you will need the real parameter to specify how you glue these things. That is called twisting parameters. Okay? So you decompose the hyperbolic surface into pairs of pans, and then you need 3G minus 3 parameters, and then you need to specify the gluing parameters. So you need another 3G minus 3 real parameter. So total 6G minus 6 parameters are needed. That is called the Fairchild-Nielsen coordinate. And you can do the same thing for real projective structures. And there's a paper written by Goldman. You can read about his Goldman parameters. But here we are dealing with 3L, SL3R, not SL2R. So even to specify, the boundary things, we need the 3 eigenvalues whose product is equal to 1. So we need 2 real parameters for each boundary curve. And then, unfortunately, the projective structures on pair of pans are not determined by specifying this like 2 real parameters on each boundary. So there are 6 real parameters for the boundary of a pair of pans, but we need more parameter. It's called internal parameter. We need 2 more real parameters to determine the projective structures on pairs of pans. Okay, so I don't care about this internal parameter right now. All I care about is how to glue these things. Okay, so for hyperbolic surface case, I only specify twisting parameters here. But here, for projective structures, I need one more parameter, twisting, and then called the bulging vertical parameters. So the Goldman called it vertical or bulging parameters. Okay. So this S here, this matrix here, is kind of a bulging vertical parameters. So when S goes to infinity, this bulging parameter goes to infinity. What's happening here is that the domain converges in Gromov-Haus topology with a base point, and if we choose a base point on the left component, so in KL, for example, it converts the convex structure of infinite volume. Why this infinite volume? because you insert this half-infinite cylinder. The length of this what is called along the, so that's S1 cross R infinity. So this S1 direction has almost the same length, but the height of this cylinder goes to infinity. So the area of this half-infinite cylinder will go to infinity. So when S goes to infinity, the area will go to infinity. Okay? And you attach this some principal triangles. For a non-separating case, if you cut along the surface, along this non-separating curve, then the limit on the one side, now if you cut along this, you have a two boundary, identical boundary. On the one boundary, you attach a half-infinite cylinder, but on the other boundary, you just left as a boundary. In that case, the bulging parameter goes to minus infinity. On this side, the bulging parameter goes to plus infinity. The sum of these two bulging parameters should equal to 0 when you glue along these things. And then you can show with an explicit calculation that I told you we sort of attach a cylinder, and the height of this cylinder grows in the order of S. Okay, so S was a bulging parameter here. So height of the cylinder is almost S. Okay, you can calculate it explicitly. You can. I wrote it down in my paper. And here I told you the area of this Hilbert area of this bulged structure goes to infinity because you attach this half infinite long cylinders. Okay, S is getting bigger and bigger along this S1 direction. The injectable radius is bounded below. Okay, now I want to calculate topological entropy of these bulged structures. But what I'm going to do is I'm going to bulge along pairs of all the curves, 3G minus 3 curves, which decompose the surface into pairs of pans. Okay, I do bulging along gamma 1, I do bulging along gamma 2, gamma 3, gamma to the 3G minus 3. Okay, and then I will show that topological entropy of this bulged structure will go to the maximum of topological entropy on pairs of pans. Okay, so I choose 3G minus 3 curves, which decompose surface into pairs of pans. And along this bulged deformation, and S goes to infinity, eventually they will kind of all these things will be separated off, and each pairs of pans will have a topological entropy, right? And because I told you, as long as the geodesic curve stays away from this bulging curve, the length is fixed throughout the deformation because that is only the conjugation. The length goes to infinity only if the curve should cross this bulging curve. If you stay away from the bulging curve, the length of this closed geodesic remains the same throughout the deformation. So for each pairs of pans, if you start from like structure 0, then there will be for example, I'm going to start from a hyperbolic structure. Okay, so each pairs of pans will have a topological entropy, which is non-zero. and I start to bulge along all this curve, then the topological entropy of this bulged structure will goes to the maximum of this topological entropy of the initial hyperbolic structures, okay, which is non-zero. So this is the kind of example where the area goes to infinity, but the topological entropy stays away from zero. One way to calculate topological entropy is just counting the number of geodesics whose length is bounded by some numbers. Okay, so this is a typical way to calculate topological entropy for a negatively curved Riemannian manifold. But the dynamics here is pseudo anaso. Same Magulus principle apply to show topological entropy is equal to the exponential growth of the closed geodesics. So you take all the geodesics, closed geodesics, whose length is less than r. You count how many there are. Because this is exponential, you take a logarithm, divide by r, take a limit. And this limit will be a topological entropy. And it is known that this is the maximal measure entropy of the geodesic flow invariant measure. And that is called Bowen-Magulus measure. Okay, let's see what happened. Fix a Pence decomposition here. First, we bulge along the first curve, gamma 1. Okay. Then here, we need to count the number of geodesic whose length is bounded by some given numbers. Then we will describe the curve, this closed curve, come in a combinatorial way. Okay, in a combinatorial way, how can I associate some combinatorial data to a closed loop? That's what I'm going to do. So once we fix the pairs of the Pence decomposition, each component of the complement is pairs of Pence. Okay, and there's a natural way to decompose these pairs of Pence into two ideal triangles. So this one wraps around here and here. This one will wraps around here and here. And the third one will wraps around here and here. Okay, did you see this picture? I think you saw it somewhere.
Yeah.
So there are.
I don't think they did, but yeah.
They did. Do you see how it is constructed? Or if you cannot see it, you just take some triangle like this, going from here, going here, and here. Okay. Imagine triangle whose vertices is here and here and here. Okay. And then you start wrapping around this thing. So you drag this part along here. It wraps around infinitely many times. It wraps around infinite many times. It wraps around infinite many times. Then you will obtain a two ideal triangle in the front and in the back. Okay. So given pairs of Pence, I associate these two ideal triangles and collect all these ideal triangles from each pairs of Pence. This is a collection of ideal triangles. For each pair of Pence, you have a two. So two times how many pairs of Pence? There are 2g minus two pairs of Pence. You can do it by calculating Euler numbers. So there are 4g minus 4 ideal triangles. I will denote it by curly tau, okay? Not titular, it's just triangulation, ideal triangulation. Then suppose I have a curve. Suppose I have a curve alpha here. I'm a very low tech person. I had a hard time to draw a picture on latex. I failed eventually. But suppose alpha is passing through these pairs of pants. Okay, so here my intention was indicate alpha was passing through, and along here it kind of wraps around, but eventually it will move on to another next curve, next pairs of pants. And here it is kind of wraps around, but it comes back. It will never escape this thing. Okay. So along each boundary, if you choose any curve, it will do one of these two. It will move on to next one, or it will stay inside this one. Okay. So it can wraps around a little bit, but eventually it'll move to next one. But here it wraps around, but it comes back. So you will see the self intersections here. But here it wraps around, but it will just you'll get on to another ones. So that's a kind of a observation. And here you. So my intention is alpha has an orientation going from above to the lower part. Okay, so alpha was traveling this way. So you choose a intersection point with one of the edge of the ideal triangle, P, and this is a succession map. Is just P maps to the second intersection point. Okay, because the edge of ideal triangle wraps around here. This map will be kind of getting denser and denser and denser, and the inverse will be. I was trying to draw here. Alpha was kind of intersecting here. That's an inverse of a succession map. Okay, and I call this segment succession inverse P and succession P. This segment will be called the crossing segment. This segment is crossing this pair of pants. After this crossing segment, here you could have either pant changing segment. So here, this guy eventually he is not faithful. He changed the pants. So he moved on to the next pants, and I call it pant changing segment. And here lower arc is a looping. It loops around, it is coming back. Okay. And I want to know how many this pant changing or looping segment loops around a cuff of this the pair of pants. So I can associate a number. Okay. Oh. By the way, combinatorially, there are at most 6 different unoriented crossing segments. So if you forget about the orientation, there will be 1, 2, 3 segment. Okay. Going from this boundary to this boundary, this boundary, this boundary, this boundary. There are 3 in the front. In the back, there's another 3. And if you count the orientation, there are almost like 12 crossing segments in each pairs of pants. Okay? Are you with me, students? So there are 3 in front, 3 in the back. So there are almost 12 is a possible oriented crossing segment in each pairs of pants. And because there are 2G minus 2 pairs of pants, there are possible kind of different 12 times 2g minus 2 different oriented crossing segment on a closed surface of sinus G. Because I want to associate some combinatorial data. Once a combinatorial data is given, you can see the homotopy type of this closed loop. That's my goal. Okay, so there is a crossing segment, and each crossing segment are joined by either looping segment or pants changing segment, right? Okay, each crossing segment is either connected by pants changing or looping segment. That's what I'm saying. Then how many times kind of this looping or pants changing wraps around a cup of pairs of pants is just simple. You just count the number of the wrapping around part. For example, if you want to measure um, looping one, we'll just take the simplest way is actually this way. Here you draw some kind of here you have yeah, here, and there's another arc here, another edge of the ideal triangulation. You connect this edge to this edge by the shortest segment between them, and you measure this looping segment is how many times it intersects these things. Okay, so this is written formally here. So DI is our length minimizing curve between two leaf of ideal triangulation. Okay. And then you can intersect, you can count how many times this guy intersected this ones. Okay. There are many ways to measure how many times this guy wraps around this thing. So for each pants changing and looping segment, this number denote how many times this segment loop around gamma I. Okay. Then, if you are given m crossing segments on the surface, you are given m crossing segment, and then you are given this number of times that either looping or pants changing segment is going around are given. This number, positive number sequence are given. Then you have to connect, pants crossing segment with this segment, and you can show there are at most 18 power of m times different closed loop in homotopy class. So if you want to see the proof, you can see the paper of Tanger and Zhang, the degeneration of convex RPT structure on surface. It proved this. Okay. So once the crossing segments are given and the sequence of these positive numbers are given, so this sequence of positive numbers tells you how many times you have to wrap around the gamma i's. Then you need to connect them. Then there are at most 18 power of m different ways. And also you have to notice that there exists a lower bound for the length of crossing segment in every pair of pants along the deformations, because you can lift this crossing segment in the universal cover, and either because it avoid the gammas, it avoid the bulging, it will lie either left or here. Okay, there's no intersection with the cuff of pants, so that will remain either here or here. But the action of the holonomic group is the same for this part. Okay, for the complement of these things, you do bulging only this. So the length of this crossing segment has a lower bound, because later I need to estimate how many curves are there whose length is bounded below by some number. I only need a lower bound to count the numbers. And also, for example, if I do the bulging, 46, I have a 15 minute, 15 minute. So along this gamma, suppose I do bulging along the first curve, gamma, and then suppose we do the, like, S goes to infinity here, the bulging parameter. Then I told you we sort of insert a cylinder along gamma whose height is in the order of S. Okay, that was the thing. And then if S goes to infinity, eventually we insert half infinite cylinder along gamma. So I modify a little bit. I take out this cylinder out of my surface. Okay, take out a cylinder C out of my surface. So from the first pant, for example, I chop off this cylinder of length in the order of S, and I have some topological pairs of pants, like P1 prime. So P1 prime together with this a cylinder with height S will be the original pairs of pants. Okay. Then I'm gonna use this P1 prime, P2, and so on. So eventually I cut off all the cylinders inserted along gamma i's and left with a new kind of a collection of pairs of pants. And I separate all this cylinder 1, cylinder 2, and cylinder 3. I take it out to estimate the length of the loop. So length of a loop or pants changing segment beta on the on here is distinct. So because the length of all the cuff of pairs of pants is unaffected by the bulging deformation, because that was just the conjugation by the some matrix. So gamma, where the bulging deformation is performed, is still they have the same holonomy. They all have the same length. So L is the kind of a minimum length of this pants cuff. And then pant changing segment beta is just suppose you have a pant changing segment along some gamma I, because it wraps around the beta times at least. The length of that pant changing or looping segment must be bigger than the length of L length of gamma I, which is bigger than L actually, times the number of times it wraps around gamma I. So this is an obvious inequality. So suppose there is a eta intersecting a gamma. So gamma is our first curve in the pairs of in the Pence decomposition. Then what's the length along the deformation is bounded below. So this is the counting the length when it wraps around either gamma I, so Pence changing or looping. And this is when it crossed the gamma. Okay. It crossed the gamma. So M is the number of crossing segment of eta. So I told you there's a universal bound, lower bound for the crossing segment. Let it called C. Then if there are M crossing segment of this eta, okay, so we decompose this eta into crossing segment and looping segment, Pence changing segment. And suppose there are M crossing segment, M times C is a lower bound for the uniform lower bound along the deformation. And now also it has suppose we do the bulging along gamma, then I told you it must cross the cylinder inserted along gamma. So the height of a cylinder was S, and this is a geometric intersection number between gamma and eta. Okay, so this is the easy things. And we do the bulging step by step for each pairs of pen, for each Pence decomposition curve. So suppose I do the bulging along Pence decomposition T. So Si is a parameter for each gamma I. Let all the Si goes to infinity. Then the claim is that topological entropy of this bulged deformation converges to this will be the topological entropy on the pair of pens and take a maximum. And this is non-zero, okay? Topological entropy of the pairs of pens is non-zero. And how do you do that? It's better to show a picture. So this was a original ideal triangulation here. And I draw one kind of crossing segment here. This crossing segment will enter into this like looping or Pence changing segments and so on. If you do the bulging deformation along gamma, you will have some inserted cylinder here of height approximately S. Okay. Now I want to change this triangulation. I push this triangulation so that it enter into the like far like distance, like here. Okay, I push this thing far into the cylinder, so that this wrapping around part only occurs around the edge of this inserted cylinder. You know, this was like S. Then I arranged that this wrapping around part only occur like S over 12 part. Then what I do is that I enlarge the length of this crossing segment. At least we will pick up like more than S over 12. Okay. So all the length of this crossing segment will go to infinity as S goes to infinity. This is what is explained. So the length of eta will sub M is the number of crossing segment, and CS is now is the length of crossing segment after I change the ideal triangulation. And I told you originally it has a lower bound, but actually the length of this thing after I changed this ideal triangulation, the crossing segment, the length of crossing segment will goes to infinity. So that is the CS. CS is goes to infinity. And here the remain the same. Okay. L is the minimum of the length of the loops in the Pence decomposition. And this is how many times it wraps around. And there's some positive part, but this positive part is sort of observed into this observation in CS, constant CS. So because this is a lower bound, it still holds. Because I want to estimate how many this crossing segment there are once the length is kind of bounded above. Suppose the length of eta is bounded above. I want to know how many there are this crossing segment is. M is below, above, bounded above by length of eta divided by CS. Okay. So here's a sort of a now final step. So first, I want to count number of geodesics whose length is less than t. Okay, t. And the curve does not entirely lie in the pair of pens. That means it must cross some pens decomposition curve. Okay, at least one. Then this is the number of such a curve is a number of such curve, because this quantity is less than this. Okay. So if this is satisfied, this is automatically satisfied by the previous one. Okay. If this is less than t, this is automatically less than t. So this is the why there's inequality here. And now, because there's an upper bound for m, there will be at most the integer part of this number crossing segment. So the crossing segment m goes from 1 to integer part of this number. Okay. But as I told you, once m crossing segments are given and the sequence of these numbers are given, then there are at most 18 power m different loops. That's why this pops up. And now, here, what is this number? This number is now how many different m crossing segments are. And I told you already there are 24g minus 24 different crossing segment, oriented crossing segment from the beginning. And now you kind of now out of that things, you form a sequence. So power of m. So there will be 24g minus 24 power of m different way to choose m crossing segment. Okay. So that's why this number pops up. And now you sort of, there are same m, so you collect the same power. Okay. Then the last step is how do you give a sequence of such a positive number k? Okay, so k was this thing. So if m crossing segments are given, we need to connect them by looping or pants changing segment, satisfying the sum of this thing is less than this one. Okay, less than this one. Sum of this thing is less than this one, less than this one. So here, you need to choose, you decompose for a given bound k, you decompose this natural number k into a different kind of positive number whose sum is equal to this thing. And this is the same as number of ways to partition all integers less than k into m non-negative integers. So that's if you write down as a function, you can show this thing goes to zero. It's just a trivial number theory. A function, this thing has an upper bound here because that is equivalent to a number of partition k into m, a positive, non-negative integers is equal to the solution of this thing. Okay. You put the k here, less than this thing, and you into m. These are non-negative, so it could be zero, but you sort of partition k into m non-negative integers, and that's a high school mathematics, and that goes to zero actually. This goes to zero actually. So you take a logarithm of this thing to calculate the exponential growth and divide by t. Then, this come here and all this thing. And this one obviously goes to zero because the CS goes to infinity. And this one, the sum of this thing also goes to zero using some trivial number theory. Okay, it's not difficult. So this part goes to zero. The number of geodesics which intersect at least one of this curve goes to zero. All the curve which survive is that the curve avoiding pants decompositions. Okay, but these pants decompositions are actually, what is this? That is the topological entropy of the pairs of pants. And by this one is also this inequality is squeezed between the two same number. So actually the topological entropy rho s converges to the maximum of these things. So this is the way how it is proved. And then you can play around that for any given number between 0 and 1, you can construct a sequence of real projective structure diverging whose topological entropy goes to alpha, starting from actually hyperbolic structure. Okay, this is the end of the talk.